Hi, my name is Frank Mitloehner and I'm here in the Department of Animal Science at UC Davis, and I want to talk about livestock and climate to you today. If you are on social media, I'm as well on Twitter, GHG Guru. Come and join me. So the topic of greenhouse gases and how they affect climate is sometimes not well understood by many audiences, and so allow me a few words just on that. What you see on this slide here is the sun radiating down solar beams to the surface of the Earth. Normally that solar radiation and the associated heat would be reflected back into space if there weren't a blanket of greenhouse gases. And greenhouse gases are gases such as methane, CO2, nitrous oxide and others. And as you can see on this slide, this blanket pretty much retains the solar radiation in our atmosphere, or at least a large part of it, and that means solar radiation and solar heat is retained and heats up the planet. And without greenhouse gases, life on this planet would be way too cold. So we need that effect, the so-called greenhouse effect. The problem is we have too many greenhouse gases. It means the blanket is getting too thick, and that means too much heat is retained. The question now is, how much do different sectors of society contribute to this greenhouse effect? And in particular for animal agriculture, how much methane? Because methane is the Achilles heel of animal agriculture. This slide here shows what's called the global warming potential of various greenhouse gases. GWP 100 is the abbreviation, and it shows how methane and nitrous oxide compare with respect to the potency to trap heat versus CO2. And so if, let's say, a source produces 10 tons of methane, all you need to do is multiply the 10 tons of methane that this source emits times this GWP 100 factor of 28. So 10 times 28 is 280 tons of CO2 equivalent, or CO2e. That's how that works. The same is true for nitrous oxide. If you have a certain amount of nitrous oxide that's emitted, you multiply that times 265, and then you achieve CO2 equivalent emissions. The problem is that this matrix, that's what it's called, GWP 100, which by the way was first invented in 1990, so 30 years ago, leaves out some very important nuances around methane, and I want to really bring some clarity to that. What you see on this slide is the global methane budget. You see here that on the left side of the slide are numerous sources of methane, including fossil fuel use, agriculture and waste, biomass burning, wetlands and others. And as you can see, when you look at this left half bubble on the left, you see that these sources amount to a total of approximately 560 teragrams of methane that are emitted globally. So 560 teragrams are emitted, but if you look closely on the right side of the slide, you see that there are also significant sinks. And these sinks amount to a total of 550 teragrams. 560 are produced, but 550 are destroyed, and that means the balance between the two is 10. Still a number that we seek to further reduce, but certainly one that's very different from just looking at the emissions alone. So when we hear about this sink or the destruction of methane, what is it? What takes place there? Well, what takes place is a so-called atmospheric removal process. There are molecules in the air that sooner or later get in contact with methane, and these molecules are called radicals. To be precise, they're called hydroxyl radicals. And when these hydroxyl radicals meet a methane molecule, they destroy it, and that happens within 10 years, approximately 10 years. And that means that methane is not just produced but also destroyed, and destroyed atmospherically by these radicals. This process is not really considered when doing the calculations with this GWP 100 unit that I talked about on my previous slide. But should it be considered? In my opinion, it should, because if a significant greenhouse gas is not just produced but also destroyed, then that makes a huge difference with respect to the accounting process. If you look at this large arrow pointing down on the sink side here, you see underneath it says sink from chemical reactions in the atmosphere. And again, remember, that is this atmospheric removal. It's called hydroxyl oxidation. Why does it matter so much? It matters because this destruction of this greenhouse gas does not occur with other greenhouse gases. It only occurs with methane. And that leads methane to be a short-lived greenhouse gas. It's called a short-lived climate pollutant. I call methane the fast and furious. Furious because it has a good punch to it, but fast because it's short-lived. And believe me, knowing about the short-lived nature of it makes all the difference in the world. As you can see on this slide here, methane has a lifespan of 10-12 years, but CO2 has one of 1,000 years. Okay? So CO2 is less potent, but it has a much longer lifespan. I will now walk you through where the carbon in the methane, the CH4 carbon, where that carbon comes from, where it originates. It all starts with photosynthesis, or the process by which plants take carbon out of the air, and then they take that carbon in the form of CO2 from the atmosphere and make it into carbohydrates. Carbohydrates such as cellulose or starch. Those carbohydrates are then ingested by a bovine, a cow let's say, and in the rumen, methanogens, methane-forming microbes do their little work and produce this gas methane, CH4. But is the carbon in this methane, in the CH4, is that carbon new and additional to our atmosphere? And the answer to that question is no. It's recycled carbon. It was in the atmosphere before in the form of CO2. So this methane here from constant sources, let's say constant cattle herds, will be produced but also destroyed almost at equal rates. Most scientists will agree today, particularly in the climate arena, that a constant source of methane, and that's important, a constant source of methane will produce methane, but also an equal amount will be destroyed. So constant source of methane is almost climate neutral. Okay? If you increase methane, then you produce more methane than is being destroyed, and that adds new additional methane, new additional warming. But if you manage to reduce methane through smart mitigation, then you can pull carbon out of the air. And that induces negative warming. And negative warming is a fancy word for cooling. So after about 10 years, this methane that's now in the air, belched out by cattle or coming from the manure, will meet these radicals, these hydroxyl radicals, and that destroys methane and converts it back to where it came from, CO2. But this CO2 is not new and additional, it is recycled, it was in the atmosphere before. So the so-called biogenic carbon cycle around cattle is very different from other sources of greenhouse gases, such as the fossil fuel sector. And I will show you how and why. But remember, the biogenic carbon cycle is one that is relatively short-lived in nature and goes around and around and around. And it has been for a long, long time. So now let's look at another source of greenhouse gases, the use of fossil fuel. So first of all, what are fossil fuels? Fossil fuels are oil, coal, gas, and they originally were plant material or animal material, animals such as dinosaurs, that populated our planet a long time ago, hundreds of millions of years ago. All that biomass that lived on Earth before then died, decayed, fossilized, accumulated underground, and over the last 70 years, 70 that is, humans extracted approximately half of all that carbon, half of that ancient carbon. We took it out of the ground, we brought it to the surface, we burned it with cars, trucks, trains, planes, ships, and now that carbon is in the atmosphere. Every time we extract new carbon from the ground and we burn it, we add new additional carbon to the atmosphere. And this is why the biogenic carbon cycle that I showed you on the previous slide versus fossil carbon are quite different. On this slide here you see them contrasted. On the left side, the fossil fuel carbon, on the right side, the biogenic carbon. Again, a one-way street on the left side, and on the right side, you see a cyclical situation where atmospheric CO2 makes it by photosynthesis into first above ground vegetation. Then those plants take the carbon that came out of the air or from the air and they put it into the ground, into the roots, and from there the carbon gets stored in the soil. A process called soil carbon sequestration. It is believed that our soils trap and capture 1/3 of all human-produced carbon. So healthy soils are a very important component in our fight against climate change. Proper ranching, proper livestock handling can intensify soil carbon sequestration because by adding manure to the soil, we enhance soil microbial activity and therefore we enhance soil carbon sequestration. What's also important here to see is that when the animals eat the above ground vegetation, yes, they belch out manure, they belch out methane, they also of course produce manure, and both sources, enteric emissions and manure, produce methane, but that is destroyed and put back into CO2. So colleagues of mine from Oxford University in the UK years ago decided that they needed to blow the whistle because the way that we quantify methane does not really take into consideration the fact that methane is a short-lived climate pollutant, that methane is not just produced but also destroyed. They said the old unit GWP 100 critically mischaracterizes the impact of that gas on warming, and they proposed a new unit, a new matrix called GWP star. But before I get to GWP star, GWP 100 overestimates the impact of constant sources of methane on warming by a factor of 4. As colleagues from Oxford have said it for years, I have said it for years, and most recently that was publicly acknowledged by the Intergovernmental Panel for Climate Change. This new unit that Oxford came up with, GWP star, is actually a unit or a matrix that takes the short-lived nature of methane into consideration, and it actually looks at the atmospheric removal of methane. And that's very important. I just told you that the IPCC, the Intergovernmental Panel for Climate Change, acknowledged that the old unit GWP 100 mischaracterizes the impact of constant sources on methane. And if you want to read that up, please go to the IPCC AR6 report. In Chapter 7, you will find on page 123 this excerpt that I put out here, which says that there's a drastic overestimation from constant sources that is the result of using this old unit GWP 100. I will show you in the next couple of slides why that really matters, okay? Because the world has been characterizing the impact of livestock methane on climate in a way that is significantly flawed and that needs to be rectified. In order to understand that, you need to understand the difference between various greenhouse gases, one being CO2, the other one being methane. I'll start with CO2. Let's imagine that you were to live about 20 miles or kilometers away from home, that you work 20 kilometers from home, and that you have to drive to work. On Monday you drive, let's say that's day one, and when you burn gas, then you put CO2 into the air. On Tuesday you drive the same distance and you put new additional carbon into the air, which is now in addition to what you put out the previous day. On Wednesday you drive again and you add new additional carbon to the existing stock from Monday and Tuesday, and to what you put into the air last week, last month, last year, last decade, to what your parents and grandparents put into the air. CO2 is a stock gas. Every time we burn fossil fuel, we add new and additional carbon to the existing stock. It is less potent than methane, but it stays in the atmosphere pretty much forever. Currently, methane is treated by most public policymakers as if it were to behave the same way as CO2. As if methane, every time it's belched out or produced from animal manure, as if every time that were to happen, we were to add new and additional methane to the atmosphere. It leaves out the fact that there is an atmospheric removal of methane. Is that a problem? Yes, it is a problem. What you see here is a depiction of how methane accumulates or not accumulates in the atmosphere. If, let's say, you have a constant source of methane, let's say a constant dairy herd or a constant beef herd, then the amount of methane produced and the amount of methane destroyed over, let's say, 20 years are roughly in balance. That makes methane a flow gas. Okay? Don't get me wrong. I'm not saying methane doesn't matter. Methane does matter. I told you it's the fast and furious. But if we have constant sources of methane, then these constant sources do not add additional carbon to the atmosphere and hence not additional warming to our climate. And if we reduce methane, if we manage to mitigate it, then we can pull carbon out of the air. And that is a real opportunity to us. I will now show you how the old unit GWP 100 versus the new GWP star compare. And I do so by showing you three scenarios. The first one is one where over 30 years we increase the amount of methane by 35%. The second scenario is one where methane is kept pretty stable. Maybe we slightly reduce it by 10%. And the third scenario is one where we reduce methane by a lot, 35%. How would the old unit GWP 100 characterize these three scenarios? It would predict that in all three cases we were to add a lot of additional CO2 equivalent emissions to our atmosphere. And that we know cannot be true, because if we have constant or decreasing sources of methane, then there can't be additional CO2 equivalent emissions. So let's see what this new unit from Oxford, GWP star, predicts for the three same scenarios. GWP star predicts that if you increase methane by a lot, you add a lot of additional warming. And that's what you see here as being blue north of the x-axis. In fact, when we increase methane, then GWP star and GWP 100 align. We do not want to add increasing amounts of methane to our atmosphere. But look what happens in the second scenario. If we hold our methane stable or slightly reduce it, then you will not see any blue north of the x-axis, and that means no additional warming. In fact, because this scenario says reduce by 10% over 30 years, which is a slight reduction, we see a little bit of blue south of the x-axis, and that means there's now a little bit of negative warming. But look what happens in the third scenario. If we reduce methane by a lot over 30 years, by 35%, then we are pulling a lot of carbon from the air. And that means we are now generating significant cooling. Now, that's a real opportunity. So the question then will be, can such a strong reduction of methane be achieved? The answer is absolutely yes. Here in California, we have probably the most aggressive regulation on methane anywhere in the world. Our farmers are mandated to reduce methane by 40%, 40. And that reduction has to happen by the year 2030, below 2013 thresholds. The legislature decided to not use the cane approach of rules and regulations and fines to make farmers reduce methane, but to use the carrot approach of using financial incentives to help farmers reduce methane. And that helped. Over the last few years, many of our farmers, dairy farmers, and we talk about large dairies, decided to cap their lagoons, to cover their lagoons and trap the biogas that's formed underneath. This technology in general is called anaerobic digestion, okay? And this is how it looks like when it's applied here in California. So they take what's called a lagoon where the manure is stored, they cover it, and they trap the biogas, 60% of which is methane. And instead of that biogas going into the air, they are now capping it, capturing it, and converting it into a fuel type called renewable natural gas. And this fuel type is then used to fuel vehicle fleets. So up until now, we are reducing about 2 million metric tons of greenhouse gases from manure management here in California. That amounts to almost a 30% reduction of methane from our dairy sector. And that's pretty revolutionary. That's incredible. I've never thought it would be possible that in just a few years, a sector as large as our dairy sector can reduce 30% of its manure-based methane. And this is what it looks like. You take the RNG from the dairy, the renewable natural gas that came from animal biogas, and you then run it into vehicles such as semi-trucks or buses or other vehicle types. And that conversion of biogas to renewable natural gas is considered the most carbon negative fuel type there is. As a result, it's strongly financially incentivized by the state with a special kind of carbon credit. It's called low carbon fuel standard credit, and that makes it financially very worthwhile to producers. In my opinion, in the next few years, we'll have many more dairies jumping onto this, reducing methane, and when doing so, pulling a lot of carbon from the air. When you reduce methane this strongly, then you're pulling so much carbon from the air that leads to a negative warming effect, i.e. cooling effect, that's offsetting other greenhouse gases that are also produced from these dairies. Overall, if methane reductions are strong enough, then they can lead a dairy to become climate neutral. Because what is pulled out of the air on the methane side offsets other greenhouse gases, leading these operations to a point where they no longer have a warming impact of these operations. So here in the dairy industry in the United States, we have seen some incredible developments over the last few years. We used to have a much larger herd of 25 million dairy cows. Today we have 9. So we went from 25 to 9 million dairy cows, but with this much smaller herd, we are producing 60% more milk. And that has led to a situation where the carbon footprint of a glass of milk in this country has now been reduced by 2/3. How? Well, there are several main tools. One of them is reproductive efficiency, which has drastically increased over the last few decades. Another one is the veterinary system, which has markedly improved. We are preventing or treating diseases that lead to better health outcomes. We have learned to improve genetic merit of both feed plants and animals. And last not least, the fourth bubble here on this slide is feed management, which has drastically improved. We now really know what to feed our cows to get optimum production. And all of these 4 tools will not just improve performance of cows, but also the environmental impact of those farms. If you want to have a little bit more information, the CLEAR Center that I'm directing has put out several documents. One of them is a white paper. You see it here on the left. It's showing how US beef and dairy can reach climate neutrality. Please don't be mistaken. This is not just something that applies to the United States. It can apply to any part of the world. It contains not just the recipe as to how you can calculate and what it means to achieve reductions with respect to climate, but also it contains Excel spreadsheets that help you do calculations for wherever you are in the world. So that's the left one, the white paper. The right one here is a YouTube video our center has put together called Rethinking Methane. It summarizes in 5 minutes what we have learned over the last few years about methane and why that really matters to you. I strongly recommend that you download and watch and share that important YouTube video. So one of the questions I get frequently is, can we eat our way out of climate change? There are people who are very much set to change what we eat because they believe that our food choices have a drastic impact on climate. So can we change climate by changing our food? Some colleagues of mine looked into what it would take for an omnivore to go vegan with respect to carbon savings. And they found that if you were to decide to go vegan for 1 year, you would reduce your carbon footprint by 0.8 tons of CO2 equivalent emissions, 0.8 tons. Now you might ask, is that a lot or not? So let's contrast that to another activity, a transatlantic flight from the United States to Europe per passenger generates 1.6 tons of greenhouse gases. So in other words, it would take you 2 years to be vegan to offset one single transatlantic flight per passenger. So now you decide whether that's a lot or not. An entire country like the United States going meatless Monday, meaning no animal source foods on 1 day a week, would reduce the carbon footprint of the United States by 0.3%. And the entire United States going vegan, no animal source foods whatsoever, which is propagated by some part of the media, if the entire country were to do that, we would reduce our carbon footprint by 2.6% of the total. So I would argue that the whole discussion around food choices and climate is largely a smokescreen, one that points us at a source, but certainly not any of the major sources. So whether you personally eat one diet over the other might have many, many different motivators, but the climate will not be changed in any major way. If you want to know what one of the greatest impacts of our food system is on the environment, it's depicted on this slide. You see here the average US family in front of all the waste, in front of all the food that's wasted. 40% of all the food produced in this country, 40% of all the food produced in all developed, and 40% of all the food produced in all developing countries never makes it through a human digestive tract. It is wasted. In the developed world, wasted at the consumer level, in our kitchens or restaurants, and in the developing countries of the third world, we speak of food losses rather than food waste, because there the majority of food is lost at the farmer level, because farmers can't harvest on time, can't transport on time, can't preserve the food in a proper way, and so on. 40% food loss, food waste is a number that applies globally. And if you were to be really concerned about the impact of our food system on climate, this would definitely be the number one issue, the largest stone to turn around and look under. So with that, I just want to point out that the CLEAR Center, we write a blog, and you might find many articles on that site under this address here. And of course, please visit us on our webpage, the CLEAR Center webpage, clear.ucdavis.edu. So with that, I thank you very much for your attention, and I hope that you learned something new. Thank you very much.